So let's see. We want to solve this equation, for example, 4, two different ways. So let's look at what these say. The first one says divide both sides by 5 first. That's the way I would recommend doing it. That's the way I did the examples on the first page. But it turns out there's two ways that are actually equivalent. So if you divide both sides by 5 first, you're going to have 5 times 7 to the x divided by 5, and then 20 divided by 5 over here. And the 5's cancel out. You end up with 7 to the power x equals 4. And this is now something where if you just have 7 to the x, you can take a logarithm of both sides. Oh, sorry, this is a 4 over here. Had a brain fart there. And the third log law says that the x can be written as multiplication in front. And to cancel out the x times that log of 7, you just divide both sides by log of 7. Okay, and that you can approximate with a calculator is log of 4 divided by log of 7 is 0.7124. Okay, so that's usually the way I recommend doing these. I want to talk about taking a log of both sides first, because there's a common mistake that I want you to watch out for. So if you take this and you take a log of both sides, log of 5 times 7 to the x, and then you do log of 20, the common mistake is saying, well, I could just take the x out right now and just write this as x times log of 5 times 7, just log of 35. That is a mistake. Those are not the same thing. So don't do that. The problem with that is you're using log law 3 when log law 3 doesn't apply to it. It wasn't just something to a power. It was two things getting multiplied. The only thing that's being raised to the power x is the 7. It's not all of this stuff raised to the power x. So log law 3 doesn't apply. But the one that does apply here, the one that applies when you have two things getting multiplied, only one of which has an exponent, is log law 1. Because you have like an a times a b, you can separate that into two logarithms. So that's the one we're going to use, is log law 1. So it's going to be log of 5 plus log of 7 to the power x. And then you have log of 20 over here. And then, let's see, now you can apply log law 3 to this. When you do that, now we can solve for x the normal way. You can subtract log of 5 from both sides, and that will leave you with x times log of 7 equals log of 20 minus log of 5. Is there a way to combine log of 20 minus log of 5? Is there a log law for that? Let's see. Oh, over here, look. If you have log of something minus something else, you could turn that into one log with those inputs divided. So this could be written as log of 20 over 5. And 20 over 5 is just 4. So we end up with kind of a longer way of getting to the same result. So I'm just going to divide both sides by log of 7 here. And that will leave you with x equals log of 20 over 5 divided by log of 7. And you're still doing log of 4 divided by log of 7 there. It's the same thing. And you'll get approximately 0.7124. Okay, so you can do either of these methods, but doing it with method B kind of takes an extra step here, because you have to use log law 1 to separate this out and then subtract that log of 5 from both sides. But it works out the same way. Okay, let's look at a few more examples. We have this equation, 6 times 2 to the power x is 20. And we want to know, is 2 to the power x greater than 1 or less than 1? And is x positive or negative? Well, let's see. If we do 6 times 1, that would be 6. So the 2 to the power x, do we want that to be bigger than 1 or less than 1? Probably bigger than 1 to make it to get something bigger than 6, because you want to get 20, which is bigger than 6. So 2 to the x is greater than 1. And if 2 to the x is greater than 1, what does that say about x? Well, let's think about making a quick table here to just remember how exponents work in general. If you do 2 to the power 0, that's always 1. 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power negative 1 is 1/2. 2 to the power negative 2 means 1 over 2 squared. That's 1/4. So if you want to get 2 to the x to be something bigger than 1 over here, then what does that say about x? X needs to be something like these positive numbers to get a result bigger than 1. So that means x is positive. So this problem is just like getting used to looking at an equation and breaking down the algebraic structure of it to think about what you know about the different parts. So how about this one? You're doing 30 times a number equals 10. So is this number 2 to the power x, 2 to the power x here, is that greater than 1 or less than 1? And what does that tell you about x? Is x positive or negative? So if we're getting 2 to the power x is multiplied by 30 and we're getting 10, if you do 30 times a number bigger than 1, you'll get something bigger than 30. If you do 30 times 1, you'll get 30. If you get 30 times something less than 1, you'll get a result less than 30. So that means 2 to the power x is less than 1. And what kinds of values of x make that happen? Well, in this case, we 2 to the power x should be like 1/3, because 30 times 1/3 is going to be 10. So what value of x gives you 1/3? Well, 1/3 is halfway between 1/2 and 1/4, sort of. So it's going to be somewhere in this range over here. So this one we can say x is negative. Okay, so this is a general sort of rule. An equation that's of this form, where you have a smaller number times a to the x is a larger number, that means that the a to the x must be greater than 1. And if a to the x is greater than 1 and a is greater than 1, for example, like a is 2, like with this example, then that means the x must be greater than 0. An equation where you have a larger number times a to the x gives you a smaller number. Making that larger number smaller, it must happen because a to the x is less than 1. And to get a to the x to be less than 1, then x has to be something like over here, something less than 0. A negative number. So that's kind of a rule that helps you get an idea of whether the solutions of an exponential equation are positive or negative. You got a few homework problems that ask you this kind of thing, like in examples 5 and 6. All right, let's do one last example for this video. You want to solve this equation. So just like with everything else, you want to get the logarithm by itself first. Just like you want to get the exponent by itself first. So I'm going to divide both sides by 4. And this, well, we don't really have like a rule for how to like take the x out of this or anything. But what can we do with that? Let's go back to the important formulas for chapter 7. Well, we have something that looks like this. Log of 10 to the, log of something equals something else. Can we just write that in the other form using just the definition of a logarithm? Yeah, what this is saying is that 2 is the exponent of 10 that results in 2x minus 6. Wait, I'm going to say 10 to the power 2. So 2 is the exponent of 10 that results in 2x minus 6. That is the definition of a logarithm. And 10 to the power 2 is just 100. Add 6 to both sides to that. Divide both sides by 2. You'll get 53 equals x. This one's a little different. You don't just have one logarithm. If you have two logarithms, we're going to need to try to get them onto the same side. I guess I'll start by moving the 2 to the other side. And then subtract the log x from both sides. So it just leaves you the 2 on the one side. But what can you do with a logarithm minus another logarithm? Is there a way to combine that? Sure there is. It's log law 2 says that a log minus a different log, you can write that as a log of x plus 198 over x. And now that you just have it as one log, you can rewrite this using the definition of a logarithm, which is that this result, this 2, is the exponent of 10 that results in x plus 198 over x. And then to solve this, well, 100 squared is, 10 squared is 100. So I'm just going to rewrite that as 100. But you could also multiply both sides by x to cancel that out. So that will leave you with 100 times x equals x plus 198. You can subtract x from both sides, and you'll get 99x equals 198. Divide both sides by 99. You'll just get x is 2. So yeah, that's a tricky kind of problem, but yeah, those log laws are going to be really useful for all of the exercises in this section and the homework. And sometimes you're going to need to use these other ones too. All right, good luck on these exercises to practice everything you learned here in this next video.